A low hum echoes across the cosmos, the actual sound of a supermassive black hole. That haunting note is a perfect introduction to the most baffling objects in existence. We are about to journey into the heart of 30 unsolved mysteries surrounding black holes and singularities. By the end, you will understand why these cosmic puzzles are the ultimate keys to unlocking the secrets of reality itself. We will confront a point of infinite density where physics breaks down and ask if everything that falls in is truly lost forever. What single question about the universe would you most want a black hole to answer for you? That haunting hum from a supermassive black hole brings us face to face with our first and most profound cosmic puzzle. What lies at the very center of a black hole? General relativity, Einstein's magnificent theory of gravity, gives us a terrifyingly simple answer: a singularity. This is a point of infinite density where all the matter that has ever fallen into the black hole is crushed into a volume of zero size. The very fabric of space and time curves to a sharp, final point, and our equations simply spit out infinities. Physics, as we know it, stops, it ceases to function. But nature abhors an infinity as much as it does a vacuum. The idea of a true, one-dimensional point is so deeply problematic that it screams we are missing a crucial piece of the puzzle. This is where our other great theory of reality, quantum mechanics, enters the stage with a furious objection. Quantum mechanics governs the bizarre world of the very small, and it insists that nothing can ever be perfectly pinpointed. There is always a fuzziness, a fundamental uncertainty. So how can everything be compressed into an infinitely small, perfectly defined point? The two pillars of modern physics, our best descriptions of the universe, give us two completely different and utterly incompatible answers for the heart of a black hole. This violent conflict is the single greatest crisis in fundamental physics, and its resolution demands a new theory, one that can marry gravity with the quantum world. We need a theory of quantum gravity to finally tell us what or what does not truly lie at the end of space-time. This violent conflict between general relativity and quantum physics births an even stranger dilemma known as the information paradox. It all started with Stephen Hawking's brilliant yet deeply troubling realization that black holes are not completely black. He discovered that due to strange quantum effects happening right at the edge of the event horizon, black holes must slowly leak radiation. They glow, they sizzle, and over immense stretches of time they evaporate, vanishing completely from the universe. This Hawking radiation, however, presents a catastrophic problem. According to everything we know about quantum mechanics, information can never be truly destroyed. If you burn a book, the information in its words is not gone forever. In principle, a being with godlike knowledge could collect every single smoke particle and trace of heat and reconstruct the entire book from the ashes. The information is scrambled, but it is preserved. Now, picture a star, a planet, or a book falling into a black hole. All that information about what fell in seems to be trapped behind the event horizon. But if the black hole later evaporates through Hawking radiation, and that radiation is completely random and featureless, carrying no information about what fell in, then where did the information go? It has been erased from existence. This violates the most sacred rule of quantum physics, creating a paradox that has divided theoretical physicists for decades. One radical solution proposes a firewall. The idea is that the event horizon is not a smooth, uneventful gateway as Einstein predicted, but a searing wall of immense energy that would instantly incinerate anything that touches it. This firewall would protect the rest of the universe from the information loss paradox by destroying the information at the horizon, but it does so by violating another core principle of relativity. So you are faced with a terrible choice. Either quantum mechanics is wrong and information can be destroyed, or general relativity is wrong and the event horizon is a deadly inferno. Neither option is acceptable. The fate of information falling into a black hole is not just an academic debate. It strikes at the heart of whether the universe is predictable and reliable at a fundamental level. If information can vanish without a trace, then the entire logical foundation of our reality is built on sand. This paradox of lost information forces us to re-examine the very nature of the event horizon itself. What exactly is this infamous point of no return? Is it a physical surface, a wall you would smash into, or is it merely a mathematical line in the sand, a boundary of information rather than substance? Classical physics, guided by Einstein's general relativity, gives us a clear and strangely peaceful answer. If you were falling into a stellar mass black hole, you would not feel a thing as you crossed the event horizon. There is no surface, no barrier. It is not a physical wall but a one-way gate in space-time, a place where the escape velocity equals the speed of light. From your perspective, you would float right through, unaware of the moment you passed the point from which you could never return. To an outside observer, however, your image would appear to freeze at the horizon, red shifted into oblivion, forever marking the edge of the known universe. This elegant picture is encapsulated by the no-hair theorem, which tells us that black holes are remarkably simple objects. No matter how complex the star or the matter that collapses to form them, a black hole can be completely described by just three properties: its mass, its electric charge, and its spin. It has no other distinguishing features, no hair, as physicists poetically say. All the intricate information about what fell in, the composition of planets, the pages of books, the history of civilizations, is seemingly erased, leaving behind a perfectly smooth, featureless horizon. But string theory, one of the leading candidates for a theory of quantum gravity, proposes a radical alternative, the fuzzball. This theory suggests that the event horizon is not a smooth, empty gateway at all. Instead, the entire interior of the black hole might be filled with a giant, tangled ball of the fundamental strings and brains that string theory posits as the building blocks of reality. The horizon, in this view, is not a sharp boundary but the fuzzy, vibrating surface of this gigantic, exotic object. There is no empty space inside, no singularity to fall towards. You would not pass smoothly through the horizon. You would collide with this dense, stringy fuzzball surface immediately. This idea resolves the information paradox by storing all the data about what fell in within the complex structure of the fuzzball itself, preventing it from being lost. So we are left with two utterly different visions of reality's ultimate edge. Is the event horizon a silent, ghostly membrane you cross without notice, leading to a mysterious interior? Or is it the hard, information-rich surface of a cosmic fuzzball, a tangible end to your journey? The true nature of this boundary remains one of the most contentious and vital mysteries in modern physics. If the event horizon is a one-way exit, could a one-way entrance exist? This brings us to the mind-bending concept of white holes. In the stark mathematics of general relativity, a white hole is the exact opposite of a black hole. Nothing, not even light, can enter a white hole while everything is violently expelled from its central singularity. It is a cosmic gusher, a fountain of space-time and matter that cannot be turned off. While black holes are the ultimate sinks, white holes would be the ultimate sources. Yet for all their mathematical elegance, we have never observed one. Most physicists believe they are unlikely to form in our universe, as they would essentially require running a black hole's collapse in reverse, violating the relentless forward march of time and entropy. They remain a beautiful, haunting possibility in our equations, a cosmic unicorn. This same mathematics that gives us black holes and white holes also opens a far more tantalizing door, the wormhole. Also known as an Einstein-Rosen bridge, a wormhole is theorized as a shortcut, a tunnel connecting two distant points in space-time. Picture the universe as a vast sheet of paper. A journey from one corner to the other is a long line across the surface. but if you could fold the paper, a wormhole would be a pencil hole punched straight through, creating an instant bridge. This is not just a spatial shortcut. It could, in theory, connect two different moments in time, making it a potential conduit for time travel. The catch, and it is a monumental one, is that the entrance to this tunnel would be a black hole and the exit would be a white hole. Furthermore, according to our current understanding, the tunnel itself would be catastrophically unstable. It would pinch shut in an instant, long before even a single photon could make the trip. To keep it open, you would need a truly exotic substance with negative energy density, something that creates a repulsive form of gravity to prop the walls of the wormhole apart. Whether such exotic matter can exist in any meaningful quantity is one of the biggest unanswered questions. So are wormholes and white holes merely mathematical phantoms, or could they be woven into the fabric of a larger cosmic reality? Some speculative theories suggest that the Big Bang itself could have been the ultimate white hole eruption, and that every black hole in our universe might pinch off to form a new, baby universe of its own, with its own white hole birth. This idea transforms our cosmos from a solitary island into a potential member of a vast multiverse, a bubbling foam of spacetime. The journey through a black hole may not end at a singularity, but at the beginning of an entirely new reality. These cosmic gateways, whether they lead to new universes or fiery walls, all begin with a simple act of collapse, but some black holes are so colossal that their very origin defies explanation. Looming at the center of nearly every galaxy, including our own Milky Way, are supermassive black holes. These are not the remains of a single dead star. They are monsters weighing in at millions, even billions of times the mass of our Sun. The deepest puzzle is not just their size, but their age. We see them blazing in the hearts of the most distant quasars, which means they were already fully formed and active when the universe was less than 1 billion years old, a mere infant by cosmic standards. This presents a monumental timing problem. How did they get so big so fast? If they started as regular stellar mass black holes, the kind formed when a giant star explodes, they would have needed to eat voraciously, non-stop, at the absolute maximum possible rate for hundreds of millions of years just to reach their observed sizes. It is like finding a fully grown ancient redwood tree sprouting from a tiny seed in what seems like only a few days. The math simply does not add up. So how did these cosmic giants get such a head start? One compelling theory points to a different kind of seed. Instead of a single star's death, imagine the direct collapse of an immense, pristine cloud of primordial gas in the early universe. Without the heavy elements that came from later generations of stars, this gas could not fragment into many small stars. Instead, under its own immense weight, the entire cloud, hundreds of thousands of times the mass of the Sun, could have collapsed directly into a massive black hole in one single cataclysmic event. This would create a heavyweight seed from the very beginning, a giant born a giant, giving it a massive advantage in the growth race. Another possibility involves a crowded stellar nursery. In the dense core of an early galaxy, many massive stars could have formed and died in rapid succession, their black hole remnants merging together or pulling in vast amounts of gas through violent interactions. It is a scenario of cosmic cannibalism where smaller black holes feast and fuse, building up mass in a frantic, chaotic dance. Yet, even this rapid assembly may not be enough to account for the very largest behemoths we see. The truth is, we do not yet know which path, or perhaps a combination of both, nature took. The rapid emergence of these supermassive black holes is a glaring clue that our models of early cosmic evolution are missing a critical chapter. What process in the infant universe could forge such immense objects with such breathtaking speed? The answer is written in the ancient light of the first quasars, a message we are still learning how to read. The violent birth of supermassive giants is mirrored on a smaller, yet equally dramatic, scale by the cosmic dance of stellar mass black holes. In 2015, humanity gained an entirely new sense for observing the universe. The LIGO and Virgo observatories did not see a collision of two black holes, they heard it. They felt the subtle shiver in space-time itself, a ripple known as a gravitational wave. When two black holes spiral inward in a final, frantic embrace, they warp the fabric of the cosmos, sending out a tremor that travels at the speed of light. By the time these waves reach Earth, they are incredibly faint, a distortion far smaller than the width of a single proton. Yet we can now detect them, and each signal tells a story of a catastrophic merger that happened billions of years ago. These events have confirmed some of Einstein's most daring predictions, but they have also unveiled profound new mysteries. The first major surprise was the mass of the black holes involved. We expected stellar mass black holes to be perhaps 10 or 20 times the mass of our Sun, the remnants of massive stars, but LIGO has detected black holes merging that are 30, 50, even 80 solar masses. These are not the corpses of regular stars, they are unexpected monsters. How do stars grow so large and leave behind such hefty remnants? This forces us to rethink the life and death of the most massive stars in the cosmos. An even deeper puzzle is how these black holes found each other in the vast emptiness of space. How does a binary pair of black holes even form? One leading theory suggests they are born together. Imagine a binary star system where two massive stars are born as partners, orbiting one another. If both are heavy enough, they could both explode as supernova and collapse into black holes, leaving behind a ready-made binary black hole pair. But there is a problem, the final parsec problem. As the two black holes spiral together, they lose energy by ejecting stars that pass nearby. However, once they get within about a parsec, a distance of just over 3 light years, the region becomes so empty of stars that this process stalls. How do they get close enough for gravitational waves to finally take over and seal their fate? They need a little help. This is where the galactic environment becomes crucial. In the dense, chaotic centers of star clusters, where thousands of stars are packed into a relatively small space, close encounters are common. A lone black hole might be gravitationally slingshotted by a passing star into the orbit of another. It is a cosmic dance orchestrated by chance, a game of gravitational billiards that can solve the final parsec problem by giving the pair the final nudge they need. Alternatively, the gas-rich environment of a galactic nucleus could provide the friction required to bring them together. The very existence of these merging pairs tells us that the universe is a far more social and interactive place than we once thought, with black holes finding each other against all odds. Each gravitational wave signal is not just a confirmation of Einstein's genius. It is a cryptic message about the violent lives and dramatic relationships of the darkest objects in the cosmos. Each gravitational wave tells a story of a final, violent merger, but it leaves one question hauntingly unanswered. What is the ultimate fate of the matter and energy that is swallowed? Once something crosses that invisible threshold, its journey is far from over, at least from a theoretical standpoint. The classical prediction is a grim and inevitable conveyor belt towards the central singularity. Every atom, every particle is stretched and torn by immense tidal forces in a process poetically called spaghettification. You would be pulled into a long, thin strand of your former self, all structure erased, on a one-way trip to be crushed into that point of infinite density, adding your mass to the black hole and then simply ceasing to be. Yet many physicists find this destiny deeply unsatisfying. It feels like an admission of defeat, a place where the universe simply gives up and stops keeping track. This has led to some of the most wild and revolutionary ideas in all of science. One breathtaking possibility is that black holes are not in points at all, but tunnels. The matter falling in might not be destroyed. Instead, it could be funneled through the black hole and violently ejected out the other side through a white hole into an entirely different universe. In this cosmic recycling model, our black holes could be the white holes of another cosmos and vice versa. This elegantly avoids the information paradox by simply shipping the problem and the matter to another reality entirely. An even more profound and widely debated theory suggests that the three-dimensional reality we experience is an illusion. This is the holographic principle. It proposes that all the information about every single particle that falls into a black hole is not lost inside, but is instead encoded on a two-dimensional surface, painted onto the event horizon itself like data on a vast cosmic hard drive. The three-dimensional space within the black hole, with its singularity and falling matter, is just a projection of this information, much like a hologram that appears to have depth but is actually created from flat, two-dimensional film. If this is true, then you, falling into a black hole, would not experience being spaghettified at all. Instead, at the moment of crossing, your entire three-dimensional existence would be transformed into a complex, scrambled code on the shimmering surface of the horizon. You would become a frozen, encoded image, a ghost in the machine of space-time. This principle might not be limited to black holes. Some physicists, like Juan Maldacena, have provided evidence that our entire universe could be operating on the same principle. The three-dimensional world we see, with its stars, planets, and people, could be a holographic projection from a two-dimensional surface at the cosmic horizon, the very edge of the observable universe. So we are left with a spectrum of fates, from the brutally simple to the mind-bendingly complex. Is matter truly annihilated at a singularity? Is it teleported to another reality? Or is it transformed into pure information, making our perceived reality a magnificent and intricate illusion? The fate of matter inside a black hole is not just a question about destruction, but a fundamental inquiry into the very nature of what reality is made of. The holographic universe theory reshapes our understanding of reality, but it also forces us to reconsider the very first moments of creation. What if the Big Bang did not just forge stars and galaxies, but also seeded the cosmos with countless invisible remnants? This leads us to the enigmatic possibility of primordial black holes. Unlike the stellar mass black holes born from dying stars or the supermassive giants in galactic centers, these would be ancient relics formed in the searing, chaotic density of the universe's first second. They could be almost any size, from as massive as an asteroid to as small as a single atom, all compressed into a microscopic point. Their existence is purely hypothetical, yet they offer a tantalizing solution to one of cosmology's greatest puzzles, dark matter. For decades, we have known that most of the matter in the universe is invisible, exerting a gravitational pull on galaxies but emitting no light. We have searched for exotic new particles to explain it with no success. Primordial black holes present an elegant, if startling, alternative. What if dark matter is not a sea of unknown particles, but a vast population of these ancient black holes, drifting unseen through the cosmos like a ghostly archipelago? The challenge, of course, is finding them. How do you detect an invisible, atom-sized object that does not interact with light? Astronomers have devised clever methods. One is gravitational microlensing. If a primordial black hole passes directly between us and a distant star, its gravity will act like a tiny lens, bending the starlight and causing the star to temporarily brighten. We have seen such events, but pinning them definitively on black holes rather than faint stars or rogue planets is incredibly difficult. The other potential signal is even more fleeting. According to Stephen Hawking's theory, the smallest black holes should be evaporating. A black hole with the mass of a small mountain would be radiating away its energy at a tremendous rate right now, ending its life in a final, spectacular burst of high-energy gamma rays. We have telescopes scanning the skies for such explosions, hoping to catch the death scream of a primordial black hole. Finding one would be a monumental discovery. It would not only solve the dark matter mystery with objects born from Einstein's gravity, but it would also provide a direct window into the conditions of the Big Bang itself. These hypothetical objects are cosmic fossils holding secrets from the very birth of space-time. The fate of matter within a black hole might not be erasure, but a cosmic rebirth on an unimaginable scale. This idea propels us from the interior of black holes to the edge of all existence, connecting them directly to the controversial and mind-expanding concept of the multiverse. Could it be that every black hole in our universe is a cosmic seed, giving birth to an entirely new universe of its own? The mathematics of general relativity allows for a stunning possibility. When matter collapses into a singularity, the tunnel or wormhole that forms inside might not lead back out into our own cosmos. Instead, it could pinch off and expand explosively into a new, self-contained spacetime, a whole new universe with its own laws of physics and its own timeline. In this breathtaking scenario, our entire cosmos, with its hundreds of billions of galaxies, might itself be the interior of a black hole existing within a much larger parent universe. Our Big Bang was not a singular, absolute beginning, but the white hole eruption from a collapsing star in another reality. This is not just a wild speculation. The physicist Lee Smolin developed a rigorous theory called cosmological natural selection, which takes this idea and gives it a profound evolutionary twist. He proposed that each universe born from a black hole inherits its fundamental physical constants, like the strength of gravity or the mass of an electron, with slight random variations from its parent. Most of these new universes would be stillborn, with constants that do not allow for the formation of atoms, stars, or black holes. But occasionally, by sheer chance, a baby universe would have just the right parameters to be fruitful, to form vast numbers of stars that then collapse into vast numbers of new black holes. Each of those black holes would then become a new universe, and the cycle repeats. In this grand cosmic Darwinism, universes that are good at making black holes are the ones that produce the most offspring. Our universe, then, is not fine-tuned for life by a divine hand, but is instead fine-tuned for black hole production. The fact that we live in a universe ripe with the stars and galaxies needed to create black holes is simply a consequence of this multiversal natural selection. We exist in a universe that is a prolific cosmic parent. This theory offers a potential answer to one of physics' deepest questions. Why do the numbers that govern our reality seem so perfectly set for our existence? The answer may be that we are merely in a universe that won the reproductive lottery. The implications are staggering. Our entire cosmic history, from the first flash of the Big Bang to the formation of our solar system, could be the intricate internal structure of a black hole in a reality we can never see or touch. Every black hole we observe could be a whole new cosmos, a budding branch on an infinite tree of reality. Are we living inside a black hole? The question forces us to confront the very nature of existence and our place within a possibly infinite cosmic lineage. Your own journey into a black hole would be a descent into a world of pure gravitational extremes. As you cross the event horizon, the pull of gravity on your feet is already unimaginably stronger than the pull on your head. This difference in force, known as a tidal force, begins to stretch you. It is a relentless cosmic tug of war, elongating your body into a long, thin stream of atoms. This is the process of spaghettification, a term as bizarre as the phenomenon it describes. You would be pulled apart not by impact or explosion, but by the sheer gradient of spacetime itself, transformed into a human-shaped strand of particles all falling in single file toward the center. But here is where the mystery deepens and reality seems to split in two, depending entirely on your point of view. From your own perspective inside the falling spaceship, this horrific stretching might not even be your immediate concern. As you fall, you would be utterly engrossed by the view. The entire history of the universe outside the black hole would appear to speed up, stars living and dying in fast forward, all the future light of the cosmos focused and funneled into a single, blindingly bright disk ahead of you. Yet for someone watching you from a safe distance with a powerful telescope, your fate would look completely different. They would never see you cross the event horizon. Instead, your image would appear to slow down, freezing at the very threshold, reddening and dimming until you fade from view entirely. This bizarre disconnect is due to one of Einstein's most famous predictions, time dilation. Gravity does not just bend space, it stretches time. The closer you get to the immense gravity of the singularity, the more drastically time slows down for you relative to the outside universe. Your final few seconds of subjective experience could span billions of years of cosmic history for everyone else. So who is right? Is your journey a swift, if violent, plunge into the unknown, or are you eternally suspended, a ghost forever etched on the edge of reality? Physics tells us that both perspectives are valid in their own reference frames, creating a paradox of experience that remains utterly unresolved. This cosmic stripping away of identity is formalized by the no-hair theorem, a name both poetic and brutally direct. It declares that a black hole, no matter how it forms, is the ultimate simpleton. All the intricate complexity of the matter that created it, the swirling gases, the shattered planets, the very atoms of ancient stars, is erased. Everything that falls in afterwards suffers the same fate, its information scrubbed away. What remains is a perfect baldness, an object described by just 3 numbers, its mass, its electric charge, and its spin. Nothing else matters. It has no other features, no hair. This is an astonishing statement. It means you could create a black hole from 1 trillion tons of pristine hydrogen or 1 trillion tons of discarded computers. And once the event horizon forms, the resulting black holes would be utterly indistinguishable if their mass, charge, and spin were identical. The universe, it seems, engages in a profound act of cosmic forgetting. But is this theorem an absolute truth, or is it a beautiful approximation that eventually breaks down? The central mystery here is whether black holes truly possess this perfect baldness, or if they secretly retain some faint imprint, some quantum fuzz of their violent past. This hidden information would be their hair. The no-hair theorem is a prediction of classical general relativity, a theory that ignores the fuzzy rules of the quantum world. When we bring quantum mechanics into the picture, the situation becomes far less clear. The information paradox we encountered earlier is a direct challenge to the no-hair idea. If information is truly lost, then the theorem holds. But if information is somehow preserved, as quantum mechanics demands, then it must be stored somewhere. Perhaps it is not stored inside the black hole, but on its surface, encoded in subtle distortions of the event horizon. This would be a form of quantum hair, a faint memory etched into the very fabric of space-time. The hunt for this hair is now entering an experimental phase, thanks to our newfound ability to listen to the universe with gravitational wave astronomy. When 2 black holes spiral together and merge, the resulting single black hole does not settle down immediately. It rings like a struck bell, vibrating in a specific set of frequencies known as its quasi-normal mode. According to the no-hair theorem, the pitch and decay of this ring-down should depend only on the final black hole's mass and spin, completely independent of what formed it. It is a pure, simple tone, but if black holes have quantum hair, if they remember the properties of the objects that formed them, then the ring-down might carry subtle harmonics, faint overtones in the gravitational chiming that betray a more complex history. Our current detectors like LIGO and Virgo are not yet sensitive enough to detect these tiny deviations, but future observatories might be. They are listening for the whisper of hair on the smoothest heads in the cosmos. Finding it would revolutionize our understanding, proving that black holes are not the simple, featureless voids of classical theory, but complex quantum objects that guard their secrets in the faintest vibrations of spacetime itself. This cosmic act of forgetting hints at a profound and unexpected connection. Black holes, the coldest objects in the universe, obey the laws of thermodynamics, the science of heat. This was a stunning revelation that reshaped physics. A black hole's event horizon has entropy. In everyday terms, entropy is a measure of disorder, of the number of ways you can rearrange the microscopic parts of a system without changing its overall appearance. A melted ice cube has higher entropy than a frozen one because its water molecules can be arranged in many more ways. For a black hole, the entropy is not about the disorder inside, but about the information we have lost about what fell in. The more massive a black hole, the larger its event horizon, and the more information it can hide. This relationship is captured by the deceptively simple Bekenstein-Hawking formula. It states that the entropy of a black hole is proportional to the area of its event horizon. This is a bizarre and profound statement. For every other system we know, entropy is related to volume. A larger box can hold more disordered gas molecules than a small one. But for a black hole, the entropy is tied to its surface area, as if all the information about everything inside is painted on its two-dimensional boundary. This was the first concrete hint of the holographic principle, the idea that our three-dimensional reality might be a projection from a two-dimensional surface. The formula itself is simple, but it conceals a monumental mystery. In statistical mechanics, the entropy of a gas is a calculable number because we know what its microscopic parts are, its atoms and molecules. We can count all the possible ways those atoms can be arranged. The Bekenstein-Hawking formula gives us the number for a black hole's entropy, a number so astronomically large it defies comprehension. But we have no idea what the microscopic pieces are that we are supposed to be counting. What are the fundamental atoms of spacetime whose different configurations give rise to this immense value? What are the individual quantum grains that make up the entropy of a black hole? Solving this mystery is the holy grail of quantum gravity research. String theory suggests these atoms could be the different vibrational states of the fundamental strings that make up the black hole. Loop quantum gravity proposes they are quantized bits of space itself, tiny loops or networks of gravity. The true answer will reveal the fundamental building blocks of reality, showing us what spacetime is truly made of at the Planck scale. The search for the atoms of a black hole's entropy is a search for the atoms of space and time. The hunt for black hole hair leads us back to that foundational crisis, the information paradox, but the debate has evolved in astonishing ways. We left off with a stark choice: accept the destruction of information and shatter quantum mechanics, or embrace a deadly firewall and break general relativity. For decades, this seemed an impossible impasse, but recent breakthroughs are weaving a third, far more subtle path toward a solution, one that relies on the ghostly connections of quantum entanglement. The key lies in a powerful new tool called the gravitational path integral, a method for calculating quantum gravitational effects. When physicists applied this math to the problem of Hawking radiation, they discovered something utterly unexpected: islands. These are not physical chunks of rock floating inside the black hole. An island is a region of spacetime inside the event horizon that, through the bizarre rules of quantum entanglement, becomes indirectly connected to the radiation streaming out. The information about what fell into the black hole is not trapped forever behind the horizon. Instead, it is not in one single place at all. It becomes shared non-locally between the interior of the black hole and the Hawking radiation that has already escaped to the outside universe. Think of it like a cosmic version of a delayed broadcast. Imagine you are watching a live event from a remote location with a terrible satellite link. The video is pixelated and the audio is garbled. It seems to carry no real information about the original event. But then, minutes later, a clear signal finally arrives, a data packet that, when combined with the earlier messy feed, suddenly restores the broadcast to perfect clarity. The complete information was never lost, it was just distributed across time. In the black hole scenario, the early, random-seeming Hawking radiation is the pixelated feed. The island is the mechanism that later delivers the clarifying data packet. The information is subtly encoded in the pattern of entanglement between the early radiation and the late radiation. As the black hole evaporates, more and more of its internal information is transferred out, painted onto the escaping radiation in this complex, non-local way. By the time the black hole is fully gone, all the information about what fell in has been faithfully, if secretly, transmitted back to the universe. This resolves the paradox without needing a firewall. From the perspective of someone falling in, the event horizon remains a smooth, peaceful gateway, preserving Einstein's vision. From the perspective of an outside physicist with a complete quantum description, no information is ever lost, preserving quantum law. The island formula shows how both can be true simultaneously. This new understanding elevates quantum entanglement from a strange microscopic curiosity to the very glue that may hold the fabric of spacetime together across a black hole's lethal boundary. We are witnessing a profound shift where the fate of information is no longer a story of destruction, but one of transformation and secret transmission across the void. These quantum threads of entanglement weave a tapestry that connects the smallest scales to the largest, tying the fate of black holes to the ultimate destiny of the cosmos itself. At the heart of that cosmic fate lies the most dominant force in the universe, a phantom presence we call dark energy. This is not a force of attraction, but of repulsion, an invisible pressure woven into the fabric of space that is causing the expansion of the universe to accelerate. For decades, dark energy and black holes have been treated as separate puzzles, one governing the vast cosmic arena, the other ruling the tiny, violent domains of collapsed stars. But what if they are intimately linked? A radical new theory suggests that black holes might not just exist within a universe expanding due to dark energy, they might be the very source of it. The central problem is the cosmological constant, the number that represents the strength of dark energy in our equations. When we try to calculate this value using quantum field theory, we get a result that is wrong by a factor of 1 followed by 120 zeros. It is the most spectacular failure of prediction in the entire history of science. This suggests we are missing something profound, and black holes could be the missing piece. The theory proposes that the accelerated expansion of the universe is not driven by some mysterious field, but is an emergent consequence of the growth of black holes. As black holes form and merge, their event horizons increase in area. According to the laws of black hole thermodynamics, this growing area is directly tied to an increase in entropy. And in an isolated system, when entropy rises, it drives expansion. Imagine the universe as a container filled with gas. If you heat that gas, its entropy increases and it expands. Now replace the gas molecules with black holes. As the universe ages, more matter collapses into black holes and existing black holes merge, constantly increasing the total entropy stored within their horizons. This relentless rise in cosmic entropy could be the engine behind the accelerating expansion we attribute to dark energy. In this view, a black hole is not a vacuum, but a storehouse of an incredible concentration of vacuum energy, the same energy inherent to empty space. The interior of a black hole, from this perspective, could be a region of repulsive gravity, a pocket of the cosmos that pushes outward rather than pulling in. While this sounds contradictory, it aligns with the mathematics of a specific type of black hole solution. Each black hole would then be a tiny seed of cosmic repulsion, and their collective growth across billions of years would manifest as the smooth, accelerating push of dark energy we observe today. This is a breathtaking unification. The darkest objects in the universe and the force that controls its ultimate fate may be two sides of the same coin. The death of stars in black holes could be the very process that breathes expansive life into the cosmos, weaving the destiny of the largest structures from the remains of the smallest. This cosmic censorship, this elegant veiling of infinities, leads us to a terrifying and thrilling possibility. What if the veil was torn away? Deep within the mathematics of general relativity, there exists a ghost, a solution that describes a singularity completely exposed to the universe. This is the naked singularity, an infinitely dense point of crushed spacetime with no event horizon to shield the cosmos from its wrath. According to Einstein's equations, such an object could form under very specific and extreme conditions, like if a black hole spun at nearly the speed of light, becoming so oblate that its event horizon pinches off at the poles, or if a cloud of dust collapsed with just the right non-spherical symmetry. The singularity would no longer be hidden in a black hole's private room. It would be out in the open, a raw wound in the fabric of reality where the known laws of physics cease to apply. The gravitational forces around it would be unimaginable and unpredictable. You could, in theory, see the singularity itself, a point of infinite density blazing against the sky. The implications of such a sight would shatter our understanding of the universe. A naked singularity would be a gateway to time travel and a destroyer of cause and effect. You could potentially fly a spaceship on a trajectory that loops around the singularity in such a twisted path that you emerge before you left. This violates causality, the fundamental principle that cause must always come before effect. The universe would become a chaotic, nonsensical place where paradoxes are born. To prevent this descent into lawlessness, the eminent physicist Roger Penrose proposed the cosmic censorship hypothesis. This is not a proven law, but a deeply held conviction that nature abhors a naked singularity. It suggests that whenever a singularity forms, the gravitational collapse will always wrap it in an event horizon, censoring it from the rest of the universe. Any process that might expose it, like a black hole spinning too fast, would be dynamically unstable and would instead result in the formation of a horizon at the last possible moment. It is as if the universe has a built-in fail-safe, a cosmic modesty curtain that drops just in time to preserve order and predictability. The hunt for a naked singularity is therefore a hunt to see if this cosmic censorship is a true law of nature or just a comforting hope. Some physicists search for their gravitational wave signatures, which would be far more violent and erratic than the clean chirp of two black holes merging. Others look for their unique shadows against bright backgrounds of gas. Finding even one would be the most revolutionary discovery in physics since relativity itself, forcing us to rewrite the rules of reality and confront a universe where the most fundamental laws are not just broken but glaringly, publicly absent. The possibility that our universe was born from a black hole is more than a speculative fantasy. It is a hypothesis grounded in a startling mathematical resemblance. Look at the equations describing the initial state of the Big Bang, and you will find they bear an uncanny similarity to those that define a singularity at the heart of a black hole. Both are points of infinite density and temperature where the known laws of physics break down completely. This parallel suggests a profound connection. Our cosmic beginning might not have been a unique, spontaneous event, but the natural outcome of a gravitational collapse in a much larger, pre-existing reality. In this view, the Big Bang was the white hole eruption from a black hole in a parent universe, a violent rebirth where a dying region of one cosmos became the fertile ground for our own. This idea naturally extends into a grander vision, the cyclic model. Imagine a cosmos without a true beginning or end, but an endless cycle of creation and destruction. In one version of this model, our universe will continue expanding until dark energy pulls every galaxy apart, leaving a cold, empty void. But within that vast emptiness, the black holes formed over billions of years remain. And given an almost infinite amount of time, even these titans will eventually evaporate through Hawking radiation. In their final moments, as they release all their stored energy and information, the conditions might become just right for a new Big Bang to ignite from the ashes of the old. The death of one cosmic epoch becomes the seed for the next. Another, more dramatic cyclic model involves the eventual reversal of the universe's expansion. If there is enough matter and dark matter, gravity could one day overcome dark energy, pulling all of space, time, and matter back together in a cataclysmic big crunch. This ultimate collapse would not be an end, but a transformation, compressing the entire universe into a state identical to the primordial singularity, which would then bounce back out in a new Big Bang. In this endless loop, every black hole formed during a universe's lifetime is a potential catalyst, a concentrated kernel of gravitational collapse that helps fuel the next great rebirth. This transforms our understanding of our place in the cosmos. We are not living in a one-off universe, but in one iteration of an infinite series, a single leaf on an eternal cosmic tree. Every black hole we see in our sky could be a universe in its own right, and our entire history might be the internal structure of a black hole in a reality we can never perceive. The search for our cosmic origins and our ultimate fate may ultimately be the same search, connected through the mysterious, life-giving death of a black hole. The smooth, classical event horizon predicted by Einstein might be the ultimate illusion. Just beneath that placid surface, the boundary of a black hole could be a maelstrom of quantum chaos. This is the seething foam of virtual particles, a concept central to our next great mystery. In the quantum vacuum of empty space, particle and antiparticle pairs constantly flicker in and out of existence, borrowing energy from the universe for a fleeting moment before they annihilate and pay back the debt. Normally, this happens entirely unseen, but at the event horizon, the immense gravitational pull changes everything. Imagine one of these virtual particles appears right at the precipice. If one particle falls in while its partner escapes, the one that escapes becomes real, carrying away energy. This is the mechanism of Hawking radiation. But this process means the event horizon is not a calm, one-way street. It is a frenetic zone of creation and destruction, a place where the fabric of spacetime itself is likely not smooth. At the tiniest conceivable scales, at the Planck length, spacetime may be a turbulent foam, constantly fluctuating and bubbling with virtual black holes and wormholes. The event horizon, where gravity is so intense, is where this quantum foam should be most pronounced. It becomes a natural laboratory, the only place in the universe where the effects of quantum gravity are magnified to a potentially detectable scale. Probing this region is our best hope for discovering the unified theory that merges gravity with quantum mechanics. How do we observe such a thing? We cannot send a probe. But we might be able to listen very carefully. The ring-down of a merged black hole, the specific frequencies at which it vibrates, could carry the faintest imprints of this quantum fizz. A perfectly smooth horizon would ring with a pure, clean tone. A foamy, quantum horizon would produce subtle distortions, a slight jitter in the signal, as if the bell itself had a textured, bubbling surface. Future gravitational wave detectors, with sensitivity far beyond our current tools, will be listening for this quantum whisper. They will be trying to hear the sound of spacetime itself churning at the edge of reality, seeking the signature of the theory that has eluded us for a century. The event horizon is not just a boundary in space, it is the frontier of fundamental physics. The quantum foam at a black hole's edge hints at a reality so fragile it might not even allow these cosmic monsters to exist. A small but serious group of physicists makes a startling claim that black holes never actually form. The central figure in this controversy is Laura Mersini-Houghton, whose calculations suggest a fatal flaw in the traditional collapse story. When a massive star runs out of fuel and collapses under its own weight, we expect it to shrink until an event horizon forms. But Mersini-Houghton argues that Hawking radiation is not a slow leak that happens after the black hole exists. Instead, she proposes that the back reaction of this radiation, the recoil from particles streaming away, begins the very moment the star starts to collapse. This outward pressure would be immense, counteracting the inward pull of gravity. In her model, the dying star would not quietly shrink into a black hole. It would put up a fight, exploding in a supernova of such unprecedented energy that it would blow itself apart completely, leaving behind no remnant, no singularity, and no event horizon. The black hole would be stillborn. The universe, according to this view, simply prohibits the formation of these paradoxical objects. The arguments against this idea are equally powerful. Critics point out that the back reaction calculations are immensely complex and rely on specific models that may not capture the full, non-linear nature of gravitational collapse. Furthermore, we have overwhelming observational evidence for objects that behave exactly like black holes. We see stars whipping around an invisible, incredibly massive object at the center of our galaxy. We have directly imaged the shadow of the supermassive object in Messier 87, and we have felt the space-time ripples from merging black holes with our gravitational wave detectors. If these are not black holes, then what are they? What bizarre, ultra-compact object could possibly mimic a black hole's gravity, its shadow, and its merger signal so perfectly? Proponents of the no black hole theory suggest they could be exotic entities like gravastars, hypothetical objects with a surface of super-dense matter and an interior of dark energy. But no such object has ever been observed, and creating a stable one that does not immediately collapse into the very black hole it seeks to replace is a monumental theoretical challenge. This debate strikes at the heart of scientific epistemology. Do we trust our mathematical models, even when they lead to a shocking conclusion that contradicts what our telescopes seem to show? Or do we trust our observations and work to fix the models that cannot yet fully describe the process? The claim that there are no black holes forces us to question not just the existence of these objects, but the very nature of evidence and the limits of our theories when pushed to the absolute extreme. The debate over black holes' very existence forces us to confront the most bizarre of their properties, their absolute dominion over time. Gravity does not just bend the path of light and matter, it warps the very fabric of time itself. The closer you get to a source of gravity, the slower time ticks relative to a distant observer. This is not a theoretical guess, it is a measured fact. The GPS satellites orbiting Earth have to constantly correct for the fact that their clocks run slightly faster than clocks on the ground, because they are in a slightly weaker gravitational field. Now amplify this effect to the extreme environment of a black hole. As you fall towards the event horizon, the gravitational time dilation becomes infinite. From the perspective of someone watching you from a safe distance, your descent would appear to slow to a crawl. Your image would freeze, redden, and fade, forever suspended at the very threshold. They would never see you cross. For you, however, time would feel perfectly normal. Your watch would tick forward second by second, and you would cross the event horizon in a finite amount of time, completely unaware of the cosmic freeze frame you have left behind. This creates a profound paradox of perspective. Both experiences are equally valid within their own frames of reference, yet they describe two mutually exclusive realities. In one, you are eternally trapped at the edge. In the other, you have already passed through and met your fate in the interior. So which one is real? This question strikes at the heart of whether time is an absolute, universal ruler or a personal, relative experience. The black hole suggests it is the latter, that your journey through time is your own, and no single clock can dictate the reality for all observers. This time warp also implies that the black hole's entire future history, from its formation to its eventual evaporation, is visible in a fast-forward blur to anyone falling in. As you descend, the light from the entire future of the universe outside would rain down upon you in a final, brilliant flash. You would witness stars dying, galaxies colliding, and the ultimate fate of the cosmos, all in the last moments of your fall. The black hole is not just a trap for matter, but a window into the future, a place where the flow of time becomes a waterfall of events. What does this tell us about time? It suggests that the orderly progression of past, present, and future may be an illusion, a local phenomenon that breaks down utterly at the edge of a black hole. Time, it seems, is not a river flowing in one direction, but a vast, frozen landscape where gravity determines the steepness of the slopes. A black hole is the bottom of the steepest valley, a place where time itself grinds to a halt for anyone watching from the hills above. This radical idea that reality is a projection originates from the seemingly infinite information capacity of a black hole. The holographic principle emerged directly from the thermodynamics of these cosmic objects, from that bizarre link between a black hole's entropy and its surface area. Remember, for a normal object, entropy scales with its volume. A larger box can hold more disordered gas molecules, but a black hole's entropy, the measure of all the information it has swallowed, is proportional only to the two-dimensional area of its event horizon. This was the first stunning clue that the information about everything inside a black hole might not be stored within its three-dimensional volume at all. It could be painted like a cosmic fresco onto its two-dimensional boundary. The physicist Gerard T. Hooft and later Leonard Susskind took this clue and ran with it, proposing a principle so revolutionary it challenges our most basic experience of the world. They suggested that this is not just a quirky property of black holes, but a fundamental law of the universe. The holographic principle states that all the information needed to perfectly describe a volume of space can be encoded on its lower dimensional boundary. Think of a standard hologram on your credit card. It looks like a three-dimensional image, but all that information is stored on a flat, two-dimensional piece of film. The depth is an illusion. The holographic principle argues that our universe operates on the same cosmic scale. The three-dimensional world we see and feel, with its stars, planets, and people, could be a magnificent projection from a vast, two-dimensional surface at the very edge of the observable universe. Every event, every particle, every force we experience here in the volume of space would be a translation of data stored on that distant, flat screen. This is not saying the universe is an illusion in the philosophical sense, but that its true, fundamental degrees of freedom are far fewer than we think, residing on a distant wall we can never touch. The mathematics supporting this is profound, with Juan Maldacén's discovery of a precise duality between a gravity-filled universe and a quantum field theory on its boundary providing a solid mathematical foundation. If this principle is correct, it means that the universe is fundamentally pixelated, with a finite amount of information that can fit within any given area. There is a limit to reality's resolution set by the Planck length. The world is not infinitely divisible, but constructed from tiny, fundamental bits of information, and we are living inside the grandest hologram of all. The holographic universe, for all its profound implications, is built on the behavior of the most colossal black holes. But there is a glaring gap in our cosmic family tree, a missing link that prevents us from tracing the full lineage from birth to behemoth. Between the stellar mass black holes, the corpses of dead stars, and the supermassive giants ruling galactic centers, there should be an entire class of intermediate mass black holes. These would be the stepping stones, weighing in at hundreds to hundreds of thousands of solar masses. They are the crucial middle children in the black hole family, and their near-total absence from our observations is one of the most frustrating puzzles in modern astrophysics. Without them, we cannot fully understand how the modest seeds of the first black holes grew into the monsters we see today. How does a black hole go from a few dozen solar masses to millions or billions? The intermediate mass class should be the evidence of that growth spurt, the teenage phase of a black hole's life, yet finding them has proven incredibly difficult. They are too massive to be formed from a single star's collapse, but not massive enough to sit in the bright, glaring core of a galaxy where they are easy to spot. So where are they hiding? One promising hunting ground is within the dense, ancient balls of stars known as globular clusters. These are celestial beehives swarming with hundreds of thousands of stars held together by gravity. In such a crowded environment, stellar mass black holes could theoretically sink to the center through gravitational interactions, merge and build up into an intermediate mass object over billions of years. We have seen tantalizing hints, like stars orbiting an invisible, massive object at the heart of some clusters, but the evidence remains circumstantial and hotly debated. Another possibility is that they are drifting in the dark, empty spaces between stars in a galaxy's halo, orphans cast out from clusters by violent gravitational encounters. Finding these lone wanderers is even harder. Why is their discovery so crucial? Because it would reveal the primary pathway of black hole growth. Did supermassive black holes get a head start from massive primordial seeds, or did they grow steadily by merging with many smaller black holes over cosmic time? If we find abundant intermediate mass black holes, especially in globular clusters, it would strongly support the merger model, painting a picture of a universe where black holes are constantly colliding and cannibalizing each other. Their absence would point toward the direct collapse model, where the first black holes were simply born huge. Each potential sighting of an intermediate mass black hole is like finding a fossil that could rewrite the evolutionary history of the cosmos's most enigmatic objects. The search for this missing link continues, a quiet hunt for the ghosts in the machine of galactic evolution. Yet these silent wanderers represent only one piece of the puzzle. The most spectacular black holes are anything but quiet. At the heart of certain active galaxies, they become cosmic engines of unimaginable power, capable of launching searing beams of matter that defy their very nature. How can an object defined by its inexorable pull become the universe's most powerful cannon? The answer lies in the mystery of relativistic jets. These are colossal, focused beams of superheated plasma that erupt from the rotational poles of some black holes, shooting across millions of light years at velocities agonizingly close to the speed of light. They are not made from material that has fallen in and somehow bounced back. Instead, they are a product of the furious dynamo created by the black hole's spin and the immense swirling disk of gas and dust that feeds it, the accretion disk. As matter spirals inward, it becomes ionized and intensely magnetic. The black hole's ferocious rotation drags the very fabric of space-time around with it, twisting these magnetic field lines into a tightly wound, colossal spring of energy. The leading theory for how this energy is tapped is the Blandford-Zenagic process. Imagine the spinning black hole and its magnetized accretion disk as a gigantic electric generator. The rotating spacetime acts like a turbine, and the magnetic field lines act like wires. This setup generates immense voltages, which in turn accelerate any stray charged particles in the vicinity to fantastic speeds. These particles are then funneled by the powerful magnetic fields into two narrow, oppositely directed beams along the black hole's rotation axis, the only path of least resistance. It is a cosmic railgun powered by the spin of a singularity. These jets are not gentle streams, they are titanic. They can carry away a significant fraction of the mass energy of the entire infalling matter, punching through intergalactic space and inflating vast, glowing lobes of radio emission that dwarf the galaxies from which they came. They can regulate star formation across entire galaxy clusters, heating surrounding gas and preventing it from cooling and collapsing into new stars. The black hole, in its feeding frenzy, becomes a master of its cosmic environment, its influence extending far beyond its event horizon. The precise mechanisms that launch and collimate these jets, however, remain one of the most active areas of research in astrophysics. We see their spectacular effects, but we are still deciphering the exact choreography of matter, magnetism, and spinning spacetime that gives them birth. The universe's dominant matter remains a ghost, but its identity might be hiding in the echoes of ancient collisions. the tantalizing possibility that dark matter is actually a vast population of primordial black holes has refused to die, evolving with each new discovery. For decades, this idea was on the fringe, struggling against tight observational limits. We knew that if too many asteroid-mass black holes drifted between stars, they would distort the light from distant sources in a way we simply did not see. These constraints seem to rule out primordial black holes as the primary component of dark matter, pushing physicists toward hypothetical particles like WIMP. But the cosmos loves a good plot twist. The detection of gravitational waves from merging black holes revitalized the entire hypothesis. When LIGO heard the first chirps of collisions involving black holes tens of times more massive than our Sun, it opened a new window. These unexpectedly heavy black holes could not be easily explained by standard stellar evolution, making them perfect candidates for ancient primordial relics. Suddenly, a specific mass window between roughly 10 and 100 solar masses became a viable hiding place for a significant fraction of the universe's missing matter. The data did not just open a door, it slammed others shut. The same gravitational wave signals have now rigorously excluded the possibility that primordial black holes in certain mass ranges, particularly between 1,000th and 1/10th of a solar mass, could make up all of dark matter. The universe is not swarming with golf ball-sized or mountain-sized black holes in the numbers required. Yet the mystery persists because the constraints are not absolute. A population of primordial black holes could still account for a portion of dark matter, perhaps teaming up with other candidates to solve the puzzle. Even more intriguingly, new mass ranges are now in play. What about black holes so small they have already evaporated, or ones so large, hundreds of thousands of solar masses, that they simply have not been found yet? The hunt has become more sophisticated, using subtle effects on the cosmic microwave background and the precise timing of pulsars to search for these ghostly objects. The connection between the darkest things in the universe and the matter that binds it together is stronger than ever. A cosmic detective story where every new gravitational wave signal is another clue. That final, silent drift toward evaporation raises a chilling question about the black hole's last breath. After radiating away for a time span longer than the current age of the universe, a black hole's mass would dwindle to almost nothing. In its final second, the Hawking radiation process would run wild, unleashing the energy of millions of hydrogen bombs in a blinding flash of high-energy particles and light. But what happens at the very end when the black hole's mass approaches the Planck mass, a tiny but fundamental unit equivalent to a speck of dust? This is the true moment of mystery, where our physics collapses into a storm of possibilities. One scenario is pure annihilation. The black hole simply radiates out of existence, vanishing completely and leaving behind nothing but empty space and a fading burst of radiation. In this view, the singularity and all its paradoxical baggage are erased from the universe for good. But quantum mechanics rebels against such a clean ending. Information cannot be destroyed, so if the black hole vanishes entirely, what happens to all the data about every star, planet, and atom it ever consumed? To preserve this cosmic ledger, another theory suggests the black hole does not vanish but leaves behind a stable, microscopic remnant, a Planck mass particle that contains all the original information locked within its structure. This remnant would be a fossil, a permanent, indestructible record of the black hole's entire history, solving the information paradox by storing the data forever. Yet the idea of such a remnant creates its own bizarre problems. An object containing an infinite amount of information in a tiny volume could have an almost infinite number of possible quantum states, making it a potential catalyst for random, vacuum destabilizing events. The vacuum of space might become an unstable sea, constantly bubbling with the ghosts of dead black holes. The most profound possibility is that the final evaporation is not an end but a new beginning. As the black hole shrinks to Planck size, the energies and densities become so extreme that they mirror the conditions of the Big Bang. In this transformative flash, the dying black hole could pinch off from our spacetime and undergo a quantum bounce, exploding outward to create a new, infant universe with its own laws of physics. Our cosmos would be a leaf on an infinite tree, with every dying black hole a seed for another reality. Each of these endings, from silent disappearance to cosmic rebirth, carries staggering implications for the nature of reality, causality, and our place in a potentially infinite chain of being. The death of a black hole may be the one event that truly reveals whether the universe forgets, remembers, or forever recreates itself. Our universe might be a three-dimensional island floating in a reality with many more hidden dimensions. This is not science fiction, but a serious proposal from string theory, and it completely transforms our understanding of black holes. In a world with extra, curled-up spatial dimensions, the nature of gravity itself could be fundamentally different on the smallest scales. This radical idea could solve one of physics' most embarrassing problems, the hierarchy problem. Why is gravity so unimaginably weaker than all the other forces? It is as if you compared the power of a single proton to the strength of the entire planet Earth. The answer might be that gravity is not weak, it is just diluted. It could be the only force that permeates all the hidden dimensions, its strength spreading thin across the full bulk of higher dimensional space, while forces like electromagnetism are confined to our familiar three-dimensional brain. This dilution would explain why gravity feels so feeble to us. But if gravity is stronger in these extra dimensions, then creating a black hole becomes terrifyingly easy. In our three-dimensional world, you need to crush a star several times more massive than our Sun to form one. But in a universe with large extra dimensions, the energies required could be within reach of a particle collider. For a fleeting moment, a high-energy collision of two protons could concentrate enough energy to warp the fabric of all dimensions, pinching off a tiny, higher-dimensional black hole right here on Earth. These would not be the classic black holes of general relativity. They might be black brains, complex membrane-like objects that vibrate and evolve in ways we can barely calculate. The most shocking prediction is that these micro-black holes would not be dangerous. They would not swallow the planet. According to Hawking's theory, they would evaporate in a flash, erupting into a shower of particles in a minuscule fraction of a second, leaving behind a clear signature in our detectors. We have looked for these signatures in the highest energy collisions at the Large Hadron Collider. So far, we have found nothing, which has placed stringent limits on the size of these potential extra dimensions. Yet the search continues because the discovery of even a single micro-black hole would be the most direct proof that our cosmos is a tiny fragment of a much larger, multidimensional reality, forever changing our place in the cosmic order. A supermassive black hole sits at the center of a galaxy like a tiny spider at the heart of a vast, spinning web. Yet this minuscule object, a mere speck compared to the hundreds of billions of stars surrounding it, holds an inexplicable power over its entire cosmic home. The most profound mystery is not that these giants exist, but that their mass is perfectly synchronized with the galaxy itself. Astronomers have discovered a tight correlation, a cosmic scaling law, linking the mass of a galaxy's central bulge of stars to the mass of its supermassive black hole. A larger bulge always hosts a heavier black hole. This is not a coincidence. It is a signature of a deep, symbiotic relationship, a billion-year tango between the smallest and largest objects in a galaxy. The question is, how do they communicate? How does a black hole buried in the chaotic core influence the serene swirl of stars tens of thousands of light-years away? The leading theory involves a dramatic cycle of feeding and feedback. When a black hole actively feeds on surrounding gas, it does not do so quietly. The infalling matter lights up as a brilliant quasar, and the black hole unleashes powerful jets and winds of radiation. This outpouring of energy acts like a cosmic regulator. It blasts through the galaxy, heating and pushing away the vast reservoirs of cold gas needed to form new stars. This process, called quenching, effectively puts the brakes on the galaxy's growth. The black hole, by feasting, ultimately starves itself and its host of future stellar generations. It is a self-limiting cycle, but there is another, more violent form of communication. When galaxies merge, their central black holes are sent careening through the new, larger galaxy, stirring up the central stellar population through their immense gravity. This gravitational stirring can funnel vast amounts of gas directly toward the black holes, triggering new feeding frenzies and further regulating star formation. The galaxy, in turn, influences the black hole by controlling the fuel supply. The density of gas in the core, the rate of stellar collisions, and the overall dynamics of the merger all dictate how much food falls onto the black hole's plate. This intricate feedback loop suggests that galaxies and their black holes did not just grow independently, they grew up together, each shaping the other's destiny across cosmic time. Yet the details of this conversation remain one of astrophysics' greatest puzzles. We see the correlation, we have theories for the mechanism, but we have not yet witnessed the entire dance from beginning to end. The black hole and its galaxy are locked in a silent, gravitational embrace, their fates forever intertwined in a mystery written across billions of years. The terrifying singularity is not the only possible destination for collapsing matter. A radical alternative emerging from the quest for quantum gravity suggests that the journey inward does not end in an infinitely dense point, but at a cosmic trampoline. This is the theory of the quantum bounce. In loop quantum gravity, one of the leading candidates to unify general relativity with quantum mechanics, space-time is not a smooth, continuous fabric. It is woven from a network of finite, indivisible loops, a tapestry of tiny, vibrating threads of reality. This granular structure prevents matter from being compressed into a true singularity. Instead, as the crushing density approaches the Planck scale, the quantum nature of space-time itself creates a powerful repulsive force. Imagine a spring being compressed. The more you push, the stronger the resistance becomes. In the heart of a collapsing black hole, the inward crush of gravity meets this ultimate quantum resistance. The collapse does not proceed to infinity, it halts and then reverses. The matter that fell in does not vanish, it rebounds, exploding outward in a dramatic reversal. This bounce would not necessarily lead back out into our own universe through the same black hole entrance. The geometry of spacetime is so twisted that the rebound could create an entirely new region of expanding spacetime, a white hole eruption birthing a new universe, or a separate, baby cosmos connected to ours only by a quantum bridge in the distant past. This single idea elegantly sidesteps the nightmarish paradoxes of the singularity. There is no point where physics breaks down, no infinite density, and no loss of information because the matter and its history are preserved through the bounce. The black hole's interior becomes a transformational chamber instead of a cosmic shredder. The universe avoids the logical dead end of a singularity by allowing for a cosmic rebirth, turning gravitational collapse into the engine of a new beginning. Could every black hole we see be a one-way tunnel to a budding universe on the other side of a quantum bounce? That first historic image of a black hole was not a photograph of the object itself. How could it be? A black hole, by its very definition, emits no light. What the Event Horizon Telescope captured was something far more ghostly and profound, a silhouette. That now iconic orange donut is actually a shadow, a dark void set against a brilliant backdrop of swirling, superheated gas. This shadow is the closest we can come to taking a picture of the event horizon. The immense gravity of the black hole warps the surrounding spacetime so severely that it acts like a colossal lens, bending the light from the accretion disk behind it and twisting it into a perfect or nearly perfect circle of darkness. The bright ring we see is that distorted light, a photon ring outlining the point of no return. But this simple image is riddled with deep mysteries. The darkness at the center is larger than the event horizon itself, a fact that tests general relativity's predictions under the most extreme conditions imaginable. The precise size and shape of this shadow depend entirely on the black hole's mass and, crucially, its spin. A perfectly circular shadow suggests a black hole that is not spinning, while a lopsided, flattened circle would reveal a rapidly rotating monster, dragging space-time around with it in a cosmic whirlpool. Analyzing the subtle asymmetries in that ring is like reading the fingerprint of the black hole's rotation. But the image also poses a puzzle about the chaotic environment it depicts. The brightness of the ring is not perfectly even. Why are some parts so much brighter than others? This uneven glow is a direct window into the frenetic, turbulent motion of the accretion disk itself. It tells us that the flow of matter spiraling inward is not a smooth, serene river, but a violent, clumpy, and magnetically dominated maelstrom. We are seeing the final furious moments of matter as it is accelerated to near light speed, just before it vanishes forever. This single image, a dark shadow framed by fire, is a laboratory for the most extreme physics. It confirms that space-time can be warped into a perfect circle, just as Einstein predicted over a century ago. Yet, it also challenges us to understand the complex, dynamic dance of matter and magnetism at the very edge of reality. Every new observation peels back another layer, forcing us to ask what other secrets are hidden within that perfect circle of darkness. This ghostly connection between entangled particles and space-time itself may be the final key to the information paradox. For decades, the puzzle seemed an impossible choice between destroying information and creating a firewall. But a breathtakingly elegant conjecture known as ER equals EPR offers a third path, weaving the fabric of reality from the threads of quantum entanglement. The letters are a nod to history. EPR refers to the Einstein-Podolsky-Rosen paradox, the famous thought experiment that first highlighted the spooky action at a distance of quantum entanglement, where two particles can share a single fate even when separated by light years. ER stands for Einstein-Rosen, the physicists who first discovered the mathematical possibility of wormholes, those space-time bridges connecting distant points. The conjecture boldly proposes that these two ideas are not just similar, they are identical. Every pair of entangled particles is not just linked by an invisible quantum thread, but by a physical, albeit microscopic, wormhole. This is not a metaphor. It suggests that the fundamental non-locality of quantum mechanics is actually a manifestation of the intricate connectivity of spacetime at the tiniest scales. Now apply this radical idea to a black hole and its Hawking radiation. As the black hole evaporates, pairs of virtual particles appear at the event horizon. One falls in, the other escapes. According to ER equals EPR, these two particles are not just an entangled pair, they are connected by a tiny wormhole. This changes everything. The interior of the black hole where the infalling particle goes is not a sealed prison. It is spatially connected through this vast network of microscopic bridges to all the Hawking radiation that has ever escaped. The information that seemingly vanished behind the horizon never actually went to a place from which it could not return. It is simply stored in the pattern of entanglement between the interior and the exterior, a pattern physically woven by these wormholes. From the outside, you see a black hole evaporating and releasing random particles. But if you could account for the entire, complex web of entanglement connecting every escaped particle to the interior, you would find that the complete information about what fell in is perfectly preserved. It is not localized in one place, it is smeared across the entire system in a profoundly non-local way. The black hole is not a safe, it is a scrambled message, and the wormholes provide the key to decoding it. This implies a reality where quantum entanglement and the geometry of spacetime are two sides of the same coin, where the spooky links between particles are literally the fabric of the cosmos. The final act of a black hole's evaporation would not be a disappearance, but a transformation, as the last remnants of the horizon dissolve to reveal a universe forever connected by a tapestry of microscopic bridges. The information was never lost, it was just hiding in the architecture of spacetime itself. That final tapestry of microscopic wormholes hints at a reality far stranger than we ever dreamed, a cosmos where spacetime itself might be forged in the quantum fires of our own laboratories. This brings us to the 30th and final mystery, one that bridges the cosmic and the terrestrial, the ultimate and the intimate. Can we create a black hole on Earth? The idea sends a shiver of both fear and fascination down the spine. It is the premise of countless disaster stories, a narrative of human hubris leading to our own destruction inside a man-made vortex. The science, however, paints a very different and far more hopeful picture. The entire concept hinges on the possibility of extraspatial dimensions, a key prediction of string theory. In our familiar three-dimensional world, the energy required to warp spacetime into a black hole is astronomical, far beyond the reach of any machine we could ever build. You would need to compress a mass several times that of our Sun into an impossibly small point. But if our universe is a three-dimensional island, a brain, floating within a higher dimensional bulk, then gravity could be fundamentally different on the smallest scales. In such a reality, gravity's incredible weakness in our world would be an illusion, a result of its force being diluted as it spreads out into these hidden dimensions. If that is true, then the energy threshold for pinching off a tiny, higher-dimensional black hole plummets. The colossal particle collisions inside the Large Hadron Collider, the most powerful machine ever built, could, in theory, be enough to create one. These would not be the gravitational monsters of deep space. They would be micro-black holes smaller than a single proton, fleeting ghosts of gravitational fury. And according to Stephen Hawking's own theory, they would not be dangerous. A black hole this small would be incredibly hot, radiating away its mass at a phenomenal rate. It would evaporate in a flash, in less than a septillionth of a second, exploding into a harmless shower of ordinary particles long before it could accrete even a single atom of matter. The vacuum of space is not empty. It is constantly seething with far more energetic particle collisions from cosmic rays that have been bombarding Earth for billions of years. If these collisions could create stable, planet-devouring black holes, the universe would have consumed itself long ago. The fact that we are still here is the most powerful evidence that such an event is impossible. The true excitement lies not in the fear but in the discovery. If the LHC were to create and detect a micro-black hole, even for an infinitesimal moment, it would be the most profound scientific discovery in history. It would be direct, irrefutable proof that our universe has more than three spatial dimensions. It would provide our first experimental window into quantum gravity and string theory, validating a whole new paradigm of physics. We would no longer be merely observers of the cosmos, but active participants, probing the very fabric of reality and creating the most extreme objects in the universe with our own hands. The creation of a black hole on Earth would not be an end, but a magnificent beginning, the moment we truly began to engineer the laws of existence. We have journeyed from the silent hum of a supermassive giant to the fleeting flash of a micro-black hole born in a particle collider. We have stood at the edge of singularities and peered across the thresholds of new universes. These 30 mysteries are not just a catalogue of cosmic curiosities. They are a single, sprawling map of our ignorance, pointing toward the next great revolution in physics. Black holes are not the end of the story, they are the very heart of it. They are not mere vacuum cleaners of space, but the universe's ultimate laboratories where the rules of reality are written and rewritten. They force us to ask if we live in a hologram, if time is an illusion, and if every moment of creation is tied to a moment of destruction. They are the key that may one day unlock the unified theory of everything, revealing the true nature of space, time, and existence. This journey does not end here. It continues with every new observation, every gravitational wave detected, and every theory proposed. Now we turn the question over to you. Which of these 30 mysteries captured your imagination most profoundly? Was it the holographic universe, the paradox of lost information, or the breathtaking possibility that we are living inside a black hole? Share your thoughts in the comments below, and if you are hungry for more deep dives into the wonders of the cosmos, be sure to subscribe. The universe is full of secrets waiting to be uncovered.